Hey everybody, let's look at this one from 1997, a uniform circular motion one. So we got this little apparatus here. We're spinning this string around. We got a 0.2 kilogram mass going around a circle of radius 0.5 meters. And that's basically it. And they got this attached to a little spring scale so it can measure how hard this string, which is attached to the mass, pulls on the spring scale there. So the very first thing that they ask us here is explain how the students, by using a timer and the information given above, could determine the speed of the ball as it's revolving. All right, so basically, this is like a lab we do in class often. Let's say we time 10 revolutions with the timer. And one of the things by timing at 10 revolutions is that has a built-in reduction of error there because we're basically doing 10 trials in a row there. So we'll time 10 revolutions with the timer. We'll find the average of that by dividing by 10. And then we will simply take our equation for velocity and for speed in this case, or since it doesn't actually have direction, and we know that that is distance over time. In this case, the distance we want is the circumference, so the time is the period, and then we'll just do 2 pi r, the radius, over the period, and that will allow us to find the speed there. So next up here, it says, explain how much work is done by the cord in one revolution and explain how you arrived at your answer. Now there's a good chance when we go over this one that we haven't covered work yet, but I'm gonna go ahead and cover it in this video. The ball, let's say, on the end of the string is moving this way at that moment, which also means that's its little bit of displacement is that way. And the force though is this way. So they're at 90 degrees to each other. And the equation for work is force times distance that it moved times the cosine of the angle between the two of those things. So that angle there is 90 degrees, and cosine of 90 degrees equals 0. So no work is done. The amount of work done is 0 joules. And why does this make sense also? Well, remember that work is equal to the change in kinetic energy. And since the kinetic energy didn't change at all, we know that that's got to be equal to 0 joules as well. So that makes sense that no work was done because the ball didn't gain any kinetic energy. All right. So next up here, it says the speed of the ball is determined to be 3.7 meters per second, assuming the cord is horizontal as it swings. Determine the tension in the cord. So all right, I'll draw a little picture right here again. There's the ball going horizontal, so we got the force of tension in towards the center over there. And we'll ignore gravity because they say that it's horizontal. So let's start these off as we do all centripetal force problems. The sum of the force is equal to mass times acceleration. And so we need to list all the forces that point towards the center. There's only one, the force of tension. And we'll do m, and we'll switch the acceleration, since it's going in a circle, to v squared over r. And then we'll just simply plug in the values that we have for this. So the force of tension is, the mass is 0.2 kilograms. The speed is 3.7 meters per second. Don't forget to square it. And we'll put that all over top of the radius, which is 0.5 meters. Work out all of that mathematics, and you'll get that the force of tension is equal to 5.476 newtons, depending upon where you decided to round there. All right, this is a long problem, so let's move on to the next part here. They say, it turns out that the actual force is 5.8 newtons on the scale. So what's the percent difference? They're unlikely to ask this question in this day and age, but we might as well go over it. Percent difference is always the difference between the two, absolute value, over their average. So we take two numbers, find out how different they are from each other, and then divide by their average. So if we just plug those numbers in here, we've got 5.8 newtons as the actual value, 5.476 newtons is what we got, and we put that over top of their average. So you add the 5.8 newtons to the 5.476 newtons, and then you take all of that and divide by 2. And if you do the mathematics there and figure it out and multiply it by 100, you'll get about 5.75%. So a percent difference is used as opposed to a percent error when you don't necessarily know which one is the more correct one. And you just want to know how far apart they are from each other. All right, so now It says the students find that despite their best efforts, they cannot swing the ball so that it remains exactly horizontal. Draw a free body diagram. All right, well, the string won't be horizontal, so it's gonna dip down, so the force of tension should go up at an angle like that, and the force of gravity should be straight down. And I tried to draw approximately the vertical component equal to the force of gravity, because that's gonna come up here again in just a second. So then it says, well, let me almost keep this here. Explain why it's not possible for the ball to swing so that the cord remains exactly horizontal. We can see it right here. There must be a vertical component of tension to cancel the force of gravity. So we've got to have that, otherwise it's impossible. All right. And then finally here, it says calculate the angle that the cord makes with the horizontal. Now this has been a while since they gave us this number. For this to work, we need to know that that tension there is the one that they told us. And so we're gonna use the force of tension is 5.8 newtons. We also know, as we just said, that there is a vertical component here. We'll call this the force of tension Y, and that's gotta be equal to the force of gravity. And since it's a 0.2 kilogram ball, then the weight of that will be 2 newtons. And so they say calculate the angle that it makes with the horizontal. So they might be talking about this angle right here. You could envision it that way. Or maybe you're picturing how much it dips below the horizontal. That won't matter because this angle and this angle are equal to each other because they're alternate interior angles. But we can see here, if I think about it this way, I've got the opposite side and the hypotenuse. So I'm gonna write that the sine of the angle is equal to the opposite side of 2 newtons over the hypotenuse, which is 5.8 newtons. And then what we will do is to find the angle, we have to take the inverse sine of each side. So 2 over 5.8. And from that, you will get that the angle is basically, depending upon how much you round it here, 20 degrees.